Hello, dear conference participants. The topic of my report is face detection for video surveillance-based security system. To date, great progress has been made in computer vision tasks, including the task of face detection. But the diversity of detection methods creates the problem of choosing the most appropriate to solve real-world problems, where there are specific requirements for accuracy, time, and conditions in which this method will work. The face recognition task itself consists of several parts. These are face detection, face alignment, feature extraction, and classification. But the main focus of this work is detection, and the aim is to find the most appropriate method that will satisfy the requirements. The purpose of this work is presented in more detail on this slide, along with the object and subject matter of the study. Also, we additionally put restrictions on the recognition system itself, which will use our chosen method in the first stage. Here they are. So we chose the following methods for testing due to the publications rating. You can see them on the current slide. In these publications, it was not specified how the quality of the methods depends on the parameters of the geometrical transformations of the faces to be fed to the input. The frame processing time was also measured on different equipment and cannot be compared. And a summary of the date of appearance of the methods, their accuracy, and the presence of landmarks of the face which the method can additionally provide is given in Table 1. So, the following experiments were chosen by which the detectors were compared. These are the dependence of detection quality on face rotation, the size of the face, and the processing speed of a single frame at VGA and HD resolutions. In the experiments, we used narrow models from publicly available repositories. For the first experiment, a synthetic dataset was created using Blender software in which the face was translated into a 3D object and rendered with a rotation of 1 degree from -90 to +90 degrees. A left-right motion plot of the different methods is shown in Figure 2. Below, the methods were additionally ranked from left to right, from less to more accurate. The same is true for up-down motion. In this case, FaceBoxes, RetinaFace, and DSFD showed the same results. Next, an experiment was conducted to test the dependence of detection quality on the face size. For this purpose, synthetic images were created with faces ranging in size from 20 to 310 pixels. These images were fed to the detectors, and an example of one result of their processing is shown on this slide. Based on the result of these experiments, a plot was made in Figure 5. Also, the detectors were ranked. Next, the detectors were compared in terms of processing speed per frame. The density of the frame processing time distribution for VGA resolutions images is shown in Figure 6. The same results were obtained for HD resolution images. The conclusions of the time comparison are presented on the current slide. The methods are ranked from slow to fast, from left to right. So, to choose the most suitable method, it was decided to compare the parameters of the methods and the results obtained according to the following criteria: average precision, presence of landmarks, the maximum range of rotation angle for which the method detects faces with a confidence of more than 90%, and the maximum face size that can be detected with a confidence of more than 90%, and finally the minimum time to process one frame for VGA images. Based on these parameters, the methods obtain the following values. See Figure 8. And based on these values, the RetinaFace mobile net method was selected. The work of the selected detection method was used in the recognition system that consisted of the following components. This slide shows an example of real-world images from which the testing dataset was created to measure the quality of recognition. So the system was tested on common metrics on this dataset, see Figure 10, and the AUC-ROC value at the optimal threshold is shown below. System architecture, technology, and detailed interaction of system components are shown on this slide. And a small illustration of how the system works. This video shows how the system recognizes a person and shows notification about it in the current interface. Finally, let's come up with some conclusions. The custom datasets have been collected for testing the following models of the robustness to face rotation, face resizing, and time costs. The system has also been tested for accuracy using the AUC-ROC on its dataset under real-world conditions. The best models in terms of rotation were RetinaFace ResNet, DSFD, and RetinaFace MobileNet. For face sizes, the best results were shown by MTCNN, DSFD, and RetinaFace ResNet models. Detection time measurements show that the fastest are RetinaFace MobileNet and FaceBoxes. In the future, conducting additional research on other stages of face recognition would be advisable. Thank you for your attention.